Hello everyone, I am Edwin, Grasshopper specialist at ShapeDiver. Welcome to the third episode of this video series where we are creating a table, a simple use case to use ShapeDiver and Grasshopper to create amazing product configurators. In this episode, we will focus on the optimization of the table model that we have created in the first and second episode, and we will touch subjects such as what is the difference between a brep and a mesh, and how to convert our breps into meshes in the most optimal way. So let's get started. So here is our Grasshopper file with our table. I made a few changes in respect to what we created in the last episode. So please check the Grasshopper file that will be in the description so that you have the updated file. The main change was this group where I actually make a calculation of the apron offsets. As we saw in the other episodes, we have these side offsets and edge offsets parameters, which control the size of this frame in respect to the tabletop. The problem with these apron parameters is that they depend on the tabletop shape, because we don't want these legs to get out of the tabletop shape. This is a geometry limit, so we should compute this in Grasshopper. So if we go, for example, to our Grasshopper file, the one that we created in the episode 1 and 2, you can see that if we have the same 50 and 50 for side offsets and end offsets, our legs are outside of the tabletop shape, something that we don't want. If we go even to 0, so this is of course something that shouldn't happen. Here in our new script, if we make this bigger or smaller, you can see that our legs always keep inside the tabletop shape. Of course, we have like a little bit of the leg out, but that's for design purposes. We could also constrain that, but for now we will keep it just like this. If we also change the corner radius, you can see that our leg always stay, at least half of it stays inside our table. So all of that calculation of the apron offsets was created here. That's in the new Grasshopper file that is in the description. So if you have any comments or questions regarding this, please leave it down below. The main important thing is that here, when we calculate the final offsets, so for example here, after we go through the definition, we can see that actually our final offsets are 87 each. So the original ones were 50 and 50, but to keep the legs inside, it has to be 87. So we want our website where we're gonna put this to know that even though our parameter is 50, our final offsets are 87. So to do that, we can use one of our ShapeDiver outputs. We have something called ShapeDiver data output, and this will be data that can be accessed via the API. So if we rename this, for example, final offsets, so the web developers that are in charge of integrating this table into a website will be able to access this information via the API using this name, final offsets. So now that we know the current state of our definition, now we can continue with the actual optimization of the model. So now we have the tabletop as a brep, apron as brep, and legs as brep. If we upload this to ShapeDiver, all of these breps will be converted into mesh automatically, because in order to render these 3D models, they have to be meshed. So for example, if we take all of this and we bake it into Rhino, and then we go into the render view and then we type what, we can see that actually to be able to render these models, they have to be converted into mesh. So you can see here the meshes that were created, so the amount of vertices and the amount of polygons. But this is not optimal, because this means that our computer is automatically converting this into a mesh. So we are not having control over how big our mesh is. We need our mesh to be as small as possible so that it downloads as fast as possible in our browser. If we have a huge mesh, then all of that mesh has to be downloaded into the browser, and that will take time. So we need to mesh this before sending to ShapeDiver, or even here in Rhino, you can see that it is also meshed automatically. So the simplest way to mesh a brep is to use the mesh brep component, and then using either the custom settings component or the speed settings component to make the meshing in the fastest way possible. Now, if we go Ctrl M, you can see here how our mesh was created. You can see all of the faces and of course the vertices connections, and then the same we can do with the other parts of the table. So for example, the apron and with the leg. So as you can see here, our legs actually take quite a while to mesh because we have 4 of them. So this is something you have to have into account when you are meshing your models, because in this case, for example, one leg, a single leg, can be meshed and then moved to the corners instead of meshing all of them at the same time. So here, instead of meshing our legs in this part, we will mesh a single one at the beginning, the unique one, and then move these meshes to our corners. So we can see there all of them. So this is a quick way of creating meshes, but actually it is not the most efficient way. If you have the plugin MetaHopper, into MetaHopper you have something called Launch Bottleneck Navigator, and this shows you which components are the ones that are taking the longest to compute. So of course, meshing takes quite a long time to compute, and all our sweeping components, cap components, so these BRAP related components are taking quite a long time to compute. So the most efficient way to create a mesh is to actually give it the instructions of how to create each phase in this mesh. So to do that, of course, we have some C# components that we created internally at ShapeDiver for our internal use, but you will be able to use them also. Again, all of these will be down in the description in the Grasshopper file, and these C# are the ones that by giving them some polylines, they will create the instructions to create our mesh. So for example, for our tabletop, we can use the loft mesh C# script. We need also the tabletop final profile curve. We need also, of course, the boundary of our tabletop. And we need a component that our CTO created a few years ago called the polyline offset component. This component takes a polyline as an input, of course an offset, but it has several parameters, but one that is important is the keep duplicates parameter. Then in this case, when a polyline starts to be offset, if it gets to a point where the segment is too small and the 2 points get to the same position, the normal Grasshopper component will delete one of these, but this component will keep both in the same position. Why? Because it is important to have the same amount of vertices in each polyline that we are going to input in the loft mesh component in order to create a clean mesh. So we need to start by converting our boundary tabletop curve into a polyline. So curve to polyline. We can give it a tolerance so that our tabletop original curve and our polyline curve are as similar as possible. So for example, we can go to 0.1 of tolerance. So this will give us more points, so more faces in our mesh. The same happens with our tabletop final profile curve. We need to convert this into a polyline as well. But in this case, we can use, for example, 0.5 because it's a smaller curve. And in this case, we just need the X and Y positions of each of the points that create this polyline. So if we go to the discontinuity component, this component will give us all these points. Then we could deconstruct the point. And with these X and Y coordinates, we can start creating our mesh. So first of all, the Y coordinates will give us our position, our layers position for our tabletop boundary polyline. So for that, we move our base polyline in Z based on the Y coordinates of the positions of our tabletop final profile. And then we offset these curves based on the X position, on the X coordinate. We offset, of course, using our component. We have to graph both. And then these moved and offset polylines will create the same shape of our profile curve. So if we use these polylines, we flatten here and then we use these polylines inside our component, that will give us our mesh with the same shape of our tabletop polyline. So if we change our tabletop profile, you can see here how it adapts to each of the tabletop profiles. And also you can see how clean our mesh is and how low poly in comparison to our mesh BRAP component it is. So the mesh BRAP, you can see here, it has way more vertices and it creates vertices in some points where it is not necessary. So for example, it creates a vertex here, it creates some vertex in the other side as well, and all of those are not necessary. Whereas in this case, it is a clean mesh based on the amount of points that we have in our boundary polyline and based on the amount of points that we have in our tabletop final profile. Now we need to create something similar to what we have here, the cap component. So to do that, we can use pufferfish. In pufferfish, we have a component called polyline to mesh, and then we can use the first and the last polyline of our offset curves list. We can merge this and convert it into a mesh. Then we have our caps here, and then we can join these two meshes and have the same result that we have in our group where we use brep components. So now if we go again to MetaHopper, to the launch bottleneck navigator, you can see here again all of our brep components in the top, whereas for example all our components, the loft mesh component is right below with just 14 milliseconds, and of course because we don't have to even mesh it anymore, so it is already a mesh, then we skip this sum up of the meshing component with the cap component with the sweep component. So this is 91 milliseconds that is taking this part, whereas this part that we created in the top just with our C# components is taking just 14 milliseconds, and some of these components take like 1 millisecond, 2 milliseconds, so super fast computation. Now we can move our tabletop mesh in the Z direction as we did with our brep, so that it is positioned in the same height. We are also going to unify our normals so that all our normals are facing into the same direction. Here you can see the difference between this and this. This is very important for reflection of light, for the texture itself that come later in another episode. Now to convert the apron to mesh directly, we can use the same mesh loft component, and it's actually easier to create this apron because it's just 4 curves, the ones that we need to use. We just need to move this with this same Z. So instead of extruding our boundary surface, we're gonna move our curves into that Z direction. And then here we have our 2 curves in the top and our 2 curves in the bottom. Then we just need to merge them. Reverse the move one and add our first curve. So the first curve will be our rectangle, our original rectangle again, to the final part of the list so that it closes our mesh. So we can see here the result. If we input this into here, you can see here our mesh. Very clean mesh and super fast to compute. Now we want to do the same for the legs brep. So to do that, we have this component which is similar to the revolution component. This component takes a polyline as the section, so it will be this section, and takes a rotation plane. So in this case we have an axis line, but in this case we are going to use a plane. So we can use the XY plane, so it will rotate around the XY plane. The domain is the same that as it works here, so of course we want it to rotate 360 degrees. Then the number of sections define how many times our base polyline will be rotated in this 360 degrees rotation. So this is basically how high poly our mesh is or low poly it is. So the more number of sections, the higher the amount of polygons that our mesh is going to have. So we can base that based on our leg thickness. It will be just x divided 2. And the UV texture size, we will see that in another episode. So we can take our final leg profile, this same part that we have here, we can move it to our new group. But of course we need to convert this into a polyline. Again, the tolerance can be in this case 0.1. This tolerance defines how many polygons our curve will have. And then we can input this in our component. So we need to convert this into a domain. And that's it. Here we have our final result. If we go again Ctrl M, we can see how many polygons there are in our mesh. And again, we can compare it against our mesh brep. So if we go again mesh brep component, we mesh this, we go speed, then we can check how many polygons this has and how many polygons this has. So if we take some panels, we can check the difference between the amount of vertices and the amount of faces. So in this case the difference is not that big, but what matters the most is the computation time. So again, in launch bottleneck navigator, this component that is called the polyline to rotational mesh is taking 34 milliseconds, whereas our mesh brep, this one is taking 78 milliseconds, plus again all the revolution component, cap component, etc, etc. So all of that sum up, whereas this one is just taking 34 milliseconds and that's it. And then of course we can do the same movement of our base mesh to the 4 corners of our apron, so that it is again positioned in these corners. So we copy paste this part and we have the same result. So now we could delete our breps groups so that they never get computed, so that they never take time of computation out of our definition. But in this case we will keep them, because we will use them for some exports options in another episode, where we will be able to export this table as a brep through ShapeDiver. And that's it. By using these 2 C# scripts that we created at ShapeDiver, you can directly go from a polyline, from the wireframe of a mesh that is based on polylines, to a mesh directly, without using brep components that normally take longer to compute. This may take longer in terms of creating the definition, but it will pay off when the users are engaging with your model, because in any website, users normally don't wait more than 5 seconds for a response from this website. So if your model is not fast to compute, then users won't wait. So that's it. This was this episode. I hope you enjoyed. I hope you learned something new. And if you did, please click in that like button down below. Remember that we will have this Grasshopper file in the description so you can download it. And if you have any comments or questions, please grab them down below. In the next episode, we will be creating some texture mapping and applying some materials to our table so that it looks realistic. And if you don't want to miss that new episode, please don't forget to subscribe so that you get the notifications. See you next time.